Hello. So in this video, what I'm going to do is go through solving simplifying radical expressions and then solving radical equations. And I'll kind of start off with just kind of one of the basic rules with this, which we'll notice that we're taking powers and then we've got roots. And if I have something that says, let's just say I use x to the power of m and I put a little letter n on the outside, this outer value is called the index. And then a way that we can simplify an expression like this is to write it as a fraction and write it as x to the power of m divided by n. So the exponent becomes my numerator, and then this index value becomes the denominator of a fraction. So just to kind of show you how it works, if we use numbers, in this case I've got x to the 3 over 5. And we can have separate expressions for this. So with part C, what I would do is realize that 8 is technically being raised to the first power. So I would rewrite this as 8 to the 1/3 and then x to the 3/3, which that is going to then simplify to 8 to the 8 to the 1/3 and then x to the 3 over 3, which is just x to the 1. So I can rewrite that as x. Something like in part E, 7 is being raised to the first power. So what I would do is rewrite this as 7 to the 1/3 power, and that is being raised to the 5th. So we can use our exponent rule of power to a power and multiply these together. 1/3 times 5 is 5/3. So you would leave this as 7 to the 5 over 3. Something like part G is also going to be a combination of the rules. I'm going to first realize that 24 is raised to the first. I can rewrite this then as 24 to the power of 1 over 6, and then x to the power of 4 over 6, and that is all raised to the 3rd. And then what I'm going to do is do my power to a power rule again. So 24, and then 1/6 times 3 is 3/6, and then x to the 4 times the 3, which is 12/6, and then we can simplify this. So I know that 3 over 6 is 1 over 2, and then 12 over 6 is really 2 over 1, or just 2. So the next problems are just going to go kind of backwards then. So what we're going to realize that the index value, again, is the denominator of these, and this would go on the outside of my radical sign. So it is the same in both fractions. So 3 is the denominator, it becomes the index value. And then on the inside of the radical, x is raised to the first, and then y is raised to the second, which again, we really don't even need the first power being written on there. It's just kind of assumed that if you don't write it, it is raised to the first. And the same kind of assumption then goes, if I just have a radical sign, we would just assume then that the number that's on the outside, my index value, would be a 2. So for example, if I did have the square root of x, you could rewrite this as technically x to the power of 1 over 2. So if you ever have like the square root of 16, for example, the square root of 16 is really 16 to the 1/2 power, and we know that the square root of 16 is 4. So 16 to the 1/2 power is then 4, which seems kind of weird. Alright, with this one, in part C, we'll notice that we have different denominators. So we can't have two different index values on the outside of the radical expression. So what I'm going to do instead is find a common denominator between both fractions, which is going to be 6. So I think about what I would have to multiply 3 by to get to 6, and that would be 2. So I would do the same thing to the numerator, double it, and then I would need to multiply this 2 by 3 to get to 6. So that's going to give me a value of 15. And then again, it becomes just like the last problem. The index value goes on the outside of the radical, and then m is raised to the 4th, and then n is raised to the 15th power. With these next ones then, what we're going to end up doing is rewriting these as a another fraction exponent, and then kind of simplify from there. So this one is going to build off the example that I just did with the square root of 16. So we know then that 16 to the 1/2 power is the same thing as saying the square root of 16. So what I'm going to do is break this up as 16 to the 1/2 raised to the third. And we'll ask ourselves kind of like, why the heck did he do that? Again, it's this notion that 16 to the 1/2 power is the same thing as taking the square root of 16. And we also know that the 1/2 times the 3 would give me the 3/2. So all that I did was break this up, and I took this value and brought it to the outside, and I threw this 1 here as my numerator. And what this allows us to do then is rewrite this as 4 to the 3rd power. And where did the 4 come from? Well, 16 to the 1/2 is, again, the same thing as saying the square root of 16, which is 4. So then what we're able to do is 4 to the 3rd power, so 4 times 4 times 4 being 64. With this problem, we're going to do this the same exact way. I'm going to take my 27 over 8, and I know that these are both perfect cubes, so I'm going to rewrite this as putting a 1/3 on the outside, and then again this squared. So what you're really doing is breaking this exponent up into 1/3 times 2, which we know is 2/3. However, I can simplify each of these expressions on the inside. So 27 to the 1/3 is really saying what is the cubed root of 27, and that is 3. And then the cubed root of 8 is saying, again, what times itself is 8, and that value is 2. So 27 over 8 to the 1/3 power just simplifies to 3 over 2. This 2 still needs to come down as an exponent. So now we can use our power to a power rule, and I can take the 3 and square it to get 9, and I can take the 2 and square it and get 4. Alright, one like this, we're going to do it the same way, even with a negative value for an exponent. I'm going to still rewrite this as 36 to the power of 1 over 2, and then that is going to be to the power of negative 3. So I did the same thing here, where we're just breaking this exponent up, because I know that 1/2 times negative 3 is negative 3/2. 36 to the 1/2 is the same thing as saying, what's the square root of 36? So that's 6. And again, what I'm really doing is raising 6 to the negative 3rd power. So I'm going to use some of our exponent rules again, and I'm going to rewrite this as 1 over 6 to the positive 3 by dropping that exponent to the denominator. And that is really 1 over 6 times 6 times 6, which is 216. So in this last example, we're going to do the same type of process. So I'm going to break apart this exponent, rewrite this as 32 to the power of 1 over 5. And then on the outside, I have negative 2. And again, recognizing that the 1/5 times the negative 2 gave me the original power of negative 2/5. And this is really asking, what is the 5th root of 32, which is 2. If I were to do 2 times 2 times 2 times 2 times 2, I would get to 32. And then I can bring this negative 2 down on the outside, use the same rule as I did for part E here, where I'm going to rewrite this as 1 over, and then that is 2 to the positive 2, which is really 1 over 4. Alright, on to these next ones. So simplifying these expressions without the use of a calculator. Same type of thing as we had just done then. So 4th root of 81 is just saying what times itself times itself times itself is 81. And that is going to be 3. I'm going to actually just go through this top row here. A number times itself, that is negative 125, is negative 5. And then the 5th root, we knew that the 5th root of 32 was 2, so then the 5th root of negative 32 would be negative 2. Now this is when we encounter some problems. If I'm looking at an even index value, so these were odd index values, and we were allowed to have a negative on the inside. If I have an even index value, we know that anytime I take a number and multiply it by itself, it's going to turn it positive, regardless of if it was positive or negative to begin with. So for something like this, there is no real answer. There's no way that I can take a number and times it by itself and make negative 64. So I'll just do one more of these bottom ones actually then, just to show you again what I could do for part E is simplify the inside expression. First, the cubed root of 8 is 2, and then I could take that 2 and raise it to the 4th power, 2 to the 4th being 16. Alright, that's good for those. I'm going to go on to the equations. So as far as solving these go, basically just to get rid of cubing something, you would take the cubed root. So what I would do is throw a little 3 on the outside of this. Again, it's asking us what number times itself is 64, and that is 4. When I have the even-powered problems, though, we will end up with a plus minus in our answer. So I'm going to demonstrate that with part B. What I would want to do first is divide both sides by 3, and that's going to give me x to the 4th equals 16. So what I would then do is take a 4th root of 16, which is saying, again, what number times itself is 16. And that's going to be 2, or it could be negative 2. If you took negative 2 and you raised it to the 4th power, you would also get positive 16. So that's why we are going to have a plus minus whenever there's an even index. And notice for part A we had an odd index on the outside of the radical, so I only had one answer. With part D, even powered, so I'm going to have a plus minus on this. I'm going to add 15 to both sides first, and that's going to give me 128. Again, we're going to isolate isolate the variable here first before I take the 6th root. So I'm going to divide both sides by 2, and that's going to give me 64. And then we are taking the 6th root of 64, which sounds kind of weird. And if I knew that before, I think we did one with 4th root of 16 is 2. If you were to multiply 16 by 2, you'd get to 32. If you do that one more time, you'd get to 64. So 2 to the 6th power is 64. Again, we do need to put a plus minus on here, though, to indicate that it could be a positive or a negative 2 for an answer. I'm going to jump down to part F, where what I'm going to do is recognize that I've got this expression that's in parentheses, raised to the 3rd power. So what I can do first is take a cubed root on both sides. And what that's going to allow me to do then is get this x plus 6 part out of the parentheses. And I'd be taking the cubed root of negative 27. Since I have an index value, it implies that I'm only going to have one answer for this. So x plus 6 is equal to, and the cubed root of negative 27 is negative 3. So if I were to do negative 3 times negative 3 times negative 3, I would get negative 27. Subtract 6 on both sides, and you'd get an x value of negative 9. And then on to part H. I'll skip over to H. Right away, take a 4th root on both sides. So I'd have 2x minus 3 is equal to the 4th root of 625. And I want to recognize that I've got this even-powered index, which implies that I have 2 answers for this. So the 2x minus 3 could either be equal to positive 5, or the 2x minus 3 could be equal to negative 5. And then we're just going to solve both of these equations. So add 3 and then divide by 2. So x equals 4 is one of my answers, and then I'm going to add 3 here and divide by 2 again, and negative 1 is my other answer. So if I were to take either of those values and substitute them in for x, I would end up getting 625. So if you took 4 times the 2, that'd give you 8. 8 minus 3 is 5, and 5 to the 4th power is 625. If I take negative 1 and I substitute it in for x, 2 times negative 1 is negative 2. Negative 2 minus 3 is negative 5, and then negative 5 to the 4th power would be negative 5 times negative 5 times negative 5 times negative 5, and would turn into a positive 625. So both of those values are going to work. And lastly, I'm just going to do one problem that would require the use of taking a cubed root or a square root. So for this example, I'm given a surface area formula. Bowling ball has a surface area of about 232 square inches, so that is the surface area. So that represents the left side of the equation. And what we want to do is determine the radius of the ball using this formula. So just showing you how we can work backwards, I'm going to divide both sides by 4 pi. So what I'm really left with is r squared is equal to, and then if you do 232 divided by 4, it comes out nice, it's 58. But I've still got this pi on the denominator. So all I did was just divide the 232 over 4, and that's simplified to this. Now we've got this idea again that if I have a square here, I can take a square root. To get this value then by itself, I end up with a radius of about 4.3 inches.